It is my pleasure to introduce our first general session speakers. David Montgomery is no stranger to our conference. He first spoke for us after the publication of his first book, Dirt, The Erosion of Civilizations. He captured our attention with the book and his presentation. He has been back twice since then. We are pleased to have David back again this year, but even more excited to welcome his wife, Ann Bikle. David and Ann have been sharing their experience connecting the soil, its biology, and the human digestive system for the last few months. The talk you're about to hear promises to challenge your thinking and connection between the soil health and human health. What they have learned in their own lives growing food and addressing health translates to the food we all grow and provide to the world. This presentation should confirm for you the importance of how we grow our food, how we nurture and restore the soil, and how we can make the difference for future generations. Ladies and gentlemen, please welcome David Montgomery and Ann Bikle.
Okay, well, many thanks for the invitation to come back here. And just to advertise, I'm Dave, not Ann. And how we're going to work this is that I'm going to do the first part of the talk, Ann's going to do the middle part, then I'll come back and do the last part. So we're kind of going to give you a talk sandwich where I get to be the bread and Ann gets to be the meat today. But what we're going to be talking about are connections between soil health and human health from really broad scales, the scales that influence civilizations, right on down to the very personal scale of what's happening inside each and every one of our gut at this very moment. And Ann and I will split that up a little bit, but we'll also be giving you sort of a guided tour through why a biologist like Ann and a geologist like myself, people who are not trained as farmers, who are not trained to think about microbes, would spend a whole lot of time in the last 10 years thinking about and researching and looking into the connections between the way microbial life influences crops and people at that full range of scales, from each and every one of us to how long our civilizations last. So if that sounds like a tall order, well, it is. That's why we got 2 hours this morning. We'll try and fit it all in. And what we're going to be doing is framing that around the series of 3 books that we wrote about. That Dirt book was the one that sort of got me into looking at the problem of soil erosion and how it's affected societies. And it's the kind of book you might expect a geologist to write. It's a backward-looking book. It looks through history, back at what has happened to the state of the land for the last few thousand years. That middle book, The Hidden Half of Nature, the one that Ann and I wrote together, is the one that guides you through our exploration of the role that microbial life plays in the health of plants and in the health of people. It was sort of our own journey of self-discovery of why it is the hidden half of nature, sort of that frames the title of this talk, is so important and has been so overlooked in both agriculture and medicine. And Growing a Revolution is the most recent one that I owe a tremendous debt to people like those of you in the room, in fact to some of you in particular in this room, in helping to teach a geologist about the finer arts of regenerative agriculture and the way agriculture really needs to be done in the future. So we're going to sort of walk through that whole thing. If you're Twitter folks, feel free to live tweet it. Our contact information and so forth is all up there. But my day job, and yes, authors need to have a day job these days. This is critical for keeping the groceries coming in. Since my day job is as a university professor, we're going to start with a quiz. There is a right answer to this quiz. The question is, which planet would you rather live on? The blue one or the red one? Blue? Anybody volunteer to go live on Mars? I have some candidates in mind, but then that's nobody in this room. Yeah, that blue planet, the one we live on, is the only planet we know of that's habitable, that can actually that can support life forms like ourselves. And so why is Earth habitable? Well, the first, and it's obvious, it's blue. There's free water on the surface of the Earth, and there's some free water on the surface of Mars, but not very much, and it's incredibly salty. Don't believe that Matt Damon movie. It would be really hard to farm on Mars. And excuse me, and if I cough a bit this morning, it's because we were just speaking at the Real Truth on Health conference where I caught a cold. So the second thing that makes Earth habitable Notice the white in the atmosphere, those clouds. We can breathe the atmosphere on Earth. It's mostly nitrogen. It's got just enough oxygen to support our form of life. It's a hospitable world. The part that gets forgotten about, well, Mars doesn't have much of an atmosphere. And what little atmosphere it has is mostly carbon dioxide. So maybe you could start terraforming it with plants, but you'd need to be geologically patient to let that play through to make that planet habitable. Notice the little scrap of brown on that picture of Earth. That's the third reason, and perhaps the most fundamental one for today, about why Earth is habitable. Earth is the only planet that we know of in the universe that has soil. You don't call the rough, rocky surface of Mars soil. That's regolith. What's the difference between soil and regolith? Thank you. Well, in part, Earth is the only planet that we know of that is the abode of life. And a lot of the regulatory systems, the environmental regulatory systems, not the legal ones, the ones that actually regulate how much oxygen is in the atmosphere, how fast soils are produced and so forth, our sort of environmental maintenance systems are run by life forms. And when Ann and I wrote the book, The Hidden Half of Nature, we were serious about that title. We were writing about microbes, things like the archaea and bacteria, the fungi, protists, and the viruses. Are they alive or not? When we wrote that book, we meant the title literally, The Hidden Half of Nature. Because if you took all the little microorganisms in the world, all the bacteria, all the fungi, on all the all your fields, in every window box in every city, in the ocean, and you weighed them all up, if you could figure out how to do that, they would weigh as much as all the plants and animals on Earth. Yet we can't see them. We can't detect them. They're fundamentally hidden from our senses. We didn't even know they existed until a Dutch draper invented little microscopes as a hobby in the 17th century and got fascinated by looking at pond water and his own spittle and whatever other fluids he could find. And he discovered things in them moving around. Microbes were considered to be real weird oddities for a long time. But we now are discovering how fundamentally important they are, not only to running environmental systems on the planet, but to our own health and the health of our crops. A single bacterium is small enough that it would take 50,000 of them to wrap around my thumb. But there's a nonillion microbes on this planet. Does anybody have any idea about how many zeros come after a 1 to make a nonillion? It's about 30. That's enough that you could take a chain of microbes and it could extend from this planet to Alpha Centauri and back. So if they would ever organize, they could get off this planet before we could. And if you look at the range of sizes in the microbial world, there's a whole diverse ecology in that hidden, invisible half of nature. So the left side of the screen is the invisible side of nature, that hidden half of nature, things that are too small for us to see with our senses. The right-hand side is what we can see with our senses. Now, geologists like to think about things in factors of 10. So what we have are sizes from the left to the right in factors of 10. So each of those bars, you're moving left to right, you're jumping up by a factor of 10 in size. And the organisms that are listed on there, just to give you an idea of what's in those size ranges. The key thing that I want to point out, though, is that look, there's 5 bars to the left, 5 bars to the right. There's as much variability in the size of organisms in the microbial world as there are between an amoeba and a human or a whale. It's an incredibly rich, diverse world full of ecosystems that lay beyond the reach of our senses. And why is this important? Particularly for this audience? Well, because as it turns out, we've been doing things for a long time that have impacted this hidden world of nature in ways that affect things that we care about. Things like soil fertility, things like our ability to grow our food, things like the ability to maintain farming practices over many generations. This is the UN's map of global soil degradation. And what it shows you is a very broad-brushed approach at looking at the state of the world's soils. You'll notice there's an awful lot of red in that map. There's places that the UN classify as dead soils, where the life in them are gone. I was talking to a gentleman from Pakistan yesterday in New York at a talk, where he was showing me pictures of what they were farming there. Beach sand that just had no organic matter in it. The life was gone. Now, I like this image that's up there on the screen now for a couple reasons. One, it's global in scope, and it shows the magnitude. There's a lot of red, there's a lot of orange on it. You kind of get the quick hit off of it that, hey, there might be a problem with the world's soils if somebody thinks this much of them are degraded. But I also like to point out that you could go into any one of those red zones on the map, and you could find farms that are building soil and they're returning degraded land to fertility. That's the story that I tell in Growing a Revolution. But I'm getting a little bit ahead of myself. But I like this map because it allows me both to paint soil degradation as a global problem, but also to say that, hey, there's ways around it, and people are already figuring it out. And there's inspirational examples of farmers around the world who have done it. Why is this important? The UN's Global State of the Soil Assessment from 2015 reported that humanity is losing about 0.3% of our collective global food production capacity each and every year to ongoing soil erosion and soil degradation. Now, 0.3%, that's kind of a small number, right? It's about what we're all getting for our savings accounts these days. It would take decades to notice the interest piling up. But if you're a geologist, you kind of think of 100 years as a round-off error on time. And if you play that 0.3% out for a century, to the year 2100 or so, we're on track to degrade a third of the world's farmland that we have today. We've already degraded a third of it. Agriculture needs to change in the 21st century if we're to avoid a colossal train wreck in terms of being able to support an agricultural civilization for the long term on the surface of the earth. We need to maintain the viability and fertility of the world's soils. The Dirt Book looks backwards at that, and if the next sort of 10 minutes or so of this talk, maybe 15 minutes, are depressing, well, so be it. The story actually is pretty depressing when you look back at the history of the world's civilizations and the way people have treated land and what that has meant for the descendants of the people who occupied that land. But then I'm going to turn it over to Anne, and she'll start sort of shining a light on the kind of science that people can use to turn this problem around. And by the time we get to the end, I hope that you will join us in thinking that this is a problem that is totally solvable on a time frame that is actually really fast, at least relative to a geologist's view of the world. And it is a collective project that humanity needs to embark upon, the regeneration of the world's soils, of the fertility of the world's soils. And the key to it all are the microbes that Anne's going to be talking a lot more about. But as I dug into researching that dirt book, the thing that really got me into thinking about soil erosion, what I realized was that soil erosion really played a role in degrading and undermining civilizations around the world, dating all the way back to early Mesopotamia. Some of the earliest agricultural societies had horrible salinization problems. Classical Greece, the Bronze Age Europe before them, the Roman Empire, the southeastern United States, Easter Island, China, the Olmecs and the Mayans in Mesoamerica. The story was very similar all around the world. The degradation of the land impacted the longevity of societies. But usually the explanation that you find in environmental history textbooks is that deforestation was the problem. That deforestation led to soil erosion, which undermined the stability of societies. Now, if there's one thing that I've seen many times in the Pacific Northwest now, where Ann and I live, it's that if you cut a tree down and you walk away, a new tree grows back pretty fast. Forests can reseed fairly easily. A lot of them are very disturbance adapted. And I started realizing in researching the Dirt Book that the culprit in the kind of soil loss that undermined whole regions of the ancient world wasn't so much the axe, but it was the plow that followed. This is where the connection to no-till plowing, no-till farming starts to become clear. Because what is it about the plow that actually led to the long-term degradation of the land? Well, think about what a plow does by inverting the soil, turning it upside down, standing it on its head, if you will. Well, one, it's good weed control, but two, it leaves the land surface bare and vulnerable to erosion by wind or rain until the next crop or the next weeds or the next forest comes in. And if you think about soil the way that somebody like me does, as a system that's produced from the breakdown of rocks, the mixing of that mineral matter with organic matter to build soil, because after all, healthy, fertile soil is the marriage of geology and biology. You can build, so how fast does nature build soils at? Anybody ever taken a rock and just set it out on the sidewalk somewhere to like see how fast you can make soil out of it? Your great-grandchildren will be continuing the experiment for you. It takes a long time, and I'll show you some numbers on that in a minute. But if you think about soil as something that's made and something that can be lost, if you think of soil erosion as how you're losing the soil, and the standing stock of soil on a hillside, that represents the natural capital that civilizations use to finance their survival and their growth. And if you have a system like that, where you a way to produce it, a way to lose it, and a standing stock of it, it's just like our bank accounts. And if you spend money faster than you make money for long enough, you burn through your savings, and I can vouch for this personally, and you can run out of money. Soil is no different considered at the level of a civilization. And we've run this experiment numerous times throughout the history of humanity. I tell those stories in the Dirt Book, and I'm going to spare you all but a couple of them today. And the one I'm going to emphasize is classical Greece. Why am I going to talk about classical Greece? Because folks back in the 1980s, when I was in college, did the geology and the archaeology, the geoarchaeology, to put together the story of what happened to the Greek landscape. And cycles of soil erosion and soil formation were triggered upon the arrival of the plow from points to the east. What did this landscape look like upon the arrival of the plow? Well, from the end of the last ice age to the arrival of the plow, so for 5,000 or 6,000 years or so, this was open oak woodland. You can basically see those little vertical stripes below the oak trees. That represents the soil. It was about 1 to 3 feet thick on the hillsides with rocks underneath. And the brown stuff down at the bottom, that's alluvium, river bottom deposits down at the bottom. So what happened when the plow arrived? Where do you think they started farming first? Well, like in many regions, they started along the rivers because it was flat, well-watered ground, relatively easily worked. It was the best farmland in those regions. And as their population grew, farming spread up onto the hillsides. And they were growing mostly wheat and crops, tilling the hillsides. And what happened over the centuries is that the soil was removed from the hillsides and it piled up down in the valley bottoms. They took a thin layer of soil, no more than like a foot or two, and piled it up down in the valley bottoms. And it took centuries to do it. What was the technology? Well, it was organic, but then it was tillage, full-on tillage. You can still find Bronze Age agricultural implements up in some of the bare rocky slopes in the southern Greek environments that we all kind of remember from those 1970s and 80s James Bond movies that were popular. Well, Tjeerd Van Andel and Chris Runnels, the geologist and the archaeologist who did this work, then went a step further. And it's when I found this diagram in one of their papers that I really started me thinking about, oh, what's the connection between soil loss and the longevity of civilizations? So what do you see on this figure? It's the population density of a particular valley in southern Greece going back to 6,000 BC. So it's the last 8,000 years of human history. He goes, there's very few places in the world where 3 successive civilizations have occupied the same piece of ground. And there's reasons for that. But notice each one of those black dots is their estimate of the population density at a different point in history. So it starts out low around 6,000 BC. The plow arrives and they're able to actually feed more people as agriculture arrives in Greece, and the population goes up in the Bronze Age. You then have a crash and the population dives in sort of the first dark age before the classical age of Greece. Then the population rises again, it crashes again after the classical age, and then it rises again to the modern age. And there's one big question that comes out looking at a figure like this. It's like, okay, you got rise, fall, rise, what's next? And is this potentially a model for the global land use? Now there's 2 characteristics of this curve as well. One of which is trivial. The trivial one is essentially, why does the amplitude of that signal rise each time through the cycle? Well, we have technology today that's far better than we did in the Bronze Age. That's really no mystery at all. You would expect that. But what sets the periodicity? Now, admittedly, this is a small sample size, but I can't find anywhere on Earth that's had 4 civilizations on the same piece of land since the dawn of agriculture. This is as good as it gets in terms of data on this issue. It started me thinking, well, do the time frames for soil loss and degradation pencil out as being able to explain the periodicity to a cycle like this? Could they contribute? Well, you know, like most academics, when I sort of was looking at this, I was thinking, wow, I'm really onto something new. Well, like, no, there's very few really new ideas in the world. The classical Greek philosopher Plato had figured out the connection between soil degradation and the longevity of societies back in the days of classical Greece, when he noticed the erosive effects of the Bronze Age soil erosion event on the landscape that he occupied. And he wrote, based on observations of things like pedestals of a tree growing on a meter high, an oak tree on a meter high pedestal of soil around a farmer's field that was the farmer's lunch favorite spot to have lunch. He would never cut it down or plow it over, but it was standing, you know, feet above the surrounding farmland. Plato recognized that the tree hadn't lifted the earth up to make its own pedestal. The fields had eroded away around it. He was looking at things like the rivers of Greece, flowing brown off of extensively tilled environments and flowing clean out of the forest. He put these pieces together and basically wrote that he thought that the Greek landscape had been degraded and couldn't support as many people as it had back in the Bronze Age. Now, I also find that it's probably best to pick on one's home state when one travels. So the next example I'm going to show you is from eastern Washington. And it's from the Palouse region, a photograph taken about in 1970. And it shows you a winter wheat field. You'll notice there's nothing on the field. It's in the fallow part of the winter wheat fallow rotation that was typical there. And it illustrates why a geologist like myself would view tillage as an environmental catastrophe. All those little channels on the landscape, those rills, you could erase them with a single pass of the plow. They're an agronomic nuisance. But they add up to big effects over time. You can wash away, you can create them with if a single storm happens at the wrong time in one's agronomic cycle. This photograph from another field, another winter wheat field in the Palouse, shows you that fence in the upper right-hand corner. That fence surrounds the farmer's water cistern that he didn't want to plow over. So it's he built a fence around it to protect it. And between 1911, when the land was first plowed, the only thing that happened between then and 1961, when the photograph was taken, was that it was planted in this wheat fallow rotation and tilled. And there's two sources of erosion from tillage erosion. One, if you always plow in the same direction on a sloping surface, you're moving soil downhill. And that can add up over time. And the second are those little rills. If they form each year, they can really add up over time as well. How big a deal is it? That's a 5-foot cliff. 5 feet of erosion in 50 years, that's a foot a decade, that's about an inch a year. There's nowhere on earth that soil forms that fast. Except my wife's garden and some of the farms that I visited. Nature doesn't build soil this fast. And that's a key lesson. But I hope you're sitting there sort of asking yourself, well, how typical is that example? That 5 feet of erosion in 50 years. It's extreme. It's the most extreme example I could find. That's why I use it. It's a great visual. It gets the point across. But you should be asking the question of how typical is it? That's one corner of one farm. Well, let's look at the American southeast. An area that stretches from Virginia up there in the upper right down to Alabama in the lower left. That gray noodle of land is the Piedmont country, the hill country. And it shows you the amount of historical soil erosion in the Piedmont region over the last several centuries. 4 to 10 inches across most of it. How big a deal is that? You go back and you read the original journals of some of the people who were first working that land. They only had about 6 to 12 inches of rich black earth over the subsoil to begin with. You go out there today, you can find lots of farms where the topsoil is gone, simply removed from the landscape, and the farmers are working the subsoil, which means, where is the native fertility of the land? It's concentrated at the surface. That's one of the pernicious problems with soil erosion. You lose the best stuff first. And if you're trap farming the subsoil, you're basically working land that is less fertile. That means you're going to be dependent on chemical supplementation to make it work. Now, I got approached a few years ago my television show called Nova, when they were in the final stages of production of a show called Making North America, where it's a 3-part series where they're trying to look at the geologic history of North America, and they basically realized they'd forgotten something, and they called me up and said, hey, is there something you could do about the soil? Because we think we need to do something. We need to cover it somehow. So could you tell the history of the soil in North America in about 3 minutes or less? And I was flummoxed for a while, wasn't quite sure what to do. Consulted with Ray Archuleta about strategy and, how do you do this? And so basically, it took him to a tobacco plantation in North Carolina, one of these places where the A horizon was gone, and took a shovel, went out, laid the white tablecloth out. That sample on the right, the khaki-looking one, that's the soil from the conventionally worked tobacco fields. It's been conventional for almost a century, I believe. It's a research farm. I'll spare you the research agency's name and acronym. But if you go off just into the woods right next door, that was a farm that was abandoned about 100, 120 years ago. And how can I tell that? Because the trees are about yay big. And you dig a hole there and compare the soil, put it on the white tablecloth right next to it. You basically have the analog for what happened to the topsoil of North Carolina. We turned the forest soil on the left into the farm soil on the right. Which would you rather be working? The khaki-colored beach sand or the rich chocolate earth that actually has life in it? And here we start to get back to the connection with microbes. Because that soil on the right isn't totally sterile, but it's on its way there. The soil on the left is more organic matter. It's got more life in it. And if we look at the estimates of how much organic matter has been lost from North American crop farmland soils averaged across the country, we've burned through about half of it, according to this paper from just a couple years ago. The soil organic matter content of many soils in North America is about 50% of the level present at the time they were converted from forests or prairies to farmlands. As we go further in this talk, and Ann talks to you about the microbial world, think of the organic matter. Think of the carbon in the soil as the currency that really keeps that system moving. It's the food that powers it. It's the batteries. We've drawn down the battery in converting the average organic matter content of a North American farmland soils from something like 5 or 6% to something like 2 or 3% or less. We've literally drained the batteries on America. And it's not just a North American problem. This shows, anybody have coffee this morning with breakfast? Nobody, amazing. This is a photograph from the heart of Costa Rican coffee country. I went down there in researching growing revolution and visited some coffee growing areas. The photograph on the left, the one with the little notebook in it, that's a photograph of the native jungle. Geologists like road cuts. We're kind of lazy. We don't dig a lot of holes. We drive around until we see what we want to see exposed on a big exposure someone else has already made for us. When you first drive into this valley, the first thing you notice looking from the mountaintop, the ridge crest going over the spine of Central America into the valley, is that the river's flowing brown. The river's flowing, it's an orangey brown. It looks like the color on the right, which we'll get to in a minute. Rivers aren't supposed to flow that color, at least not rivers, small rivers in tropical forests. They're bleeding topsoil. You go to the jungle, they still have about 6 to 12 inches of actually decent rich black earth over the subsoil, which is kind of orangey because it's oxidized because it's in the tropics. You go to the coffee plantations that have only been worked for 100 years, look at the photograph on the right. Where's the topsoil? There ain't none. It's gone. It used to be like the picture on the left. In just 100 years, they stripped it off. I hope that I'm starting to convince you that it's not so crazy to think about the problem of the plow. Played out over generations and centuries can quite literally strip the topsoil off the landscape to the degree that it actually really affects our ability to support ourselves. This is the story that I pursued in the Dirt Book, and I'm going to show you exactly sort of one more abstract example through an experiment that I did with our university's library. One of the nice things about working at a major research university is you have great access to a library that can kind of get you anything you want. And so I did, after having looked at the state of civilizations around the world and looked at the archaeology, looked at the history, you don't really have data from back in Roman times. Nobody was publishing in journals about how much sediment was bleeding off of central Italy in Roman times. And if they did, they'd be in Latin anyway. So how do you actually calibrate and think about, well, do the timescales we were talking about make sense in terms of being able to strip the soil off the landscape? We have a lot of data today. So I spent about 3 weeks one summer, and I went into the library, and I tried to vacuum up all the data I could find on how fast do the world's farmland soils erode, how fast do the world's soils build naturally, how fast do landscapes erode under native vegetation, and how fast do landscapes erode over geological time. And this is something that it's impossible to do with a simple Google search. You will not find all this stuff that way. You have to actually get them to haul those things they call books out of the basement, and journals, and actually read them and open them and extract data from them. I'm going to show you one data-intensive slide, and that's basically this slide here where I've compiled all that data into a single format. What we've done is looked at, there's different types of measurements over there on the left-hand side. And the numbers in parentheses after those words that describe what we'll talk about in a moment, those are the number of peer-reviewed academic studies that I found in the literature that had data that I could extract to generate the averages on the right-hand side of the screen. So, conventional farming, by that I mean conventional full-on tillage and fertilizer applications, almost 500 studies, 450 or so. The average rate at which the world's farmlands were eroding, based on this comparison, is about 1.5 millimeters a year, that red number up there. That's kind of a slow number, right? Your fingernails grow 10 times faster than that. San Andreas Fault moves 10 times faster than that. And then all hell breaks loose. But that's a different story. That number, 1.5 millimeters per year, translates into take about 20 years to lose an inch of soil. That's starting to sound a little more serious, right? 20 years to lose an inch of soil on average globally. Now, what's the rate at which nature builds soils? Well, that soil production numbered up there, that 0.02 millimeters a year, 2% of a millimeter a year. That translates into 1,000 years to make an inch of soil. Nature makes soil really slowly. Soil erodes really fast off of tilled fields. Therein lies the problem. Notice that the long-term rates of erosion under native vegetation up there and long-term geological erosion rates are pretty similar to long-term rates of soil production. And you might have guessed that based on our simple experience in this world, where when you go out, if you're not above timberline and you're not in the Arctic, most of the world is covered with soil of some kind. Geologic time is pretty unforgiving. If soil erosion was faster than soils built naturally over geologic time, we'd be living on Mars. There would be no soil at the surface. It all would have been removed. Conversely, if soil production was faster than soil erosion over geologic time, we'd be buried in the stuff. And it's reassuring that over the long term, this compilation suggests the numbers are balanced. That puts the difference between that red number and those blue numbers in kind of scary perspective. It's probably very real, and we've been eroding soils at least 10, if not 100 times faster than they're being built naturally. The good news is buried down there at the bottom, that erosion rate for no-till farming. Notice I've painted it blue. That rate I don't think is really distinguishable with this kind of a coarse, thick analysis from those other blue numbers. In other words, we know how to farm in ways that can solve the soil erosion problem. It's called no-till farming. This is why one of the reasons I'm happy to be speaking at a conference like this. The bad news is that it's not called conventional farming. So far I've given you all the data you would need to calculate for yourself how long an agricultural civilization would last. Because that 1 millimeter, if you give me 1 millimeter a year of net erosion of soil off of farm fields, and I could argue for 1.5 millimeters, so let's be conservative, give me 1 millimeter a year, it would take only 500 to 1,000 years to strip a 0.5 meter to 1 meter thick soil right off the hillsides. A 1 to 3 foot thick soil. Guess what? That's what the Greeks and Romans did. And all those other civilizations I talked about in the dirt book. But I also hope you're sitting there thinking, well, but what about like the Nile? They've farmed there for thousands of years in Egypt. What about the rivers of lowland China? The Indus and the Brahmaputra in India. The Tigris and Euphrates in Mesopotamia, the original Garden of Eden. Farming has been sustained there for thousands of years. How'd they pull that off? Well, all those examples are from societies that were developed on major river floodplains. And the answer is hidden right there in that word. What happens on a floodplain? It floods. And do floods bring clean water? No, floods bring silt, sand, your neighbor's tires, all kinds of things. And recall anyone care to guess how thick a grain of sand is? It's about 1 millimeter to 2 millimeters, medium to coarse sand. In other words, you could deposit a single grain of sand on a floodplain every year and it would fully offset the average long-term effect of tillage erosion. This is how you can get away with farming the Tigris and Euphrates and the Nile and the Indus and the Brahmaputra, etc., for thousands of years, because they're naturally quite resilient terrain. It puts into perspective the problem when tillage spreads outside of floodplains onto sloping surfaces, even fairly gentle ones. And so at this point, in writing the dirt book, I actually struggled very hard in writing the last chapter of the dirt book, because I tend to be an optimist by inclination and force of will, but I started to ask the question of, is soil restoration possible? And can we actually reverse the long-term pattern? And the version of the dirt book that you'll read in the last chapter is actually my third attempt at writing a not completely depressing ending to the book. But I've learned a lot over the succeeding 10 years. Some of what I've learned is thanks to folks like you in the audience, farmers who've shared their wisdom and experience with me. But an awful lot of it was from experience I gained watching what Ann did in our yard. So at this point, I'm going to turn it over to her to talk about the hidden half of nature and the microbial world. And the first thing we need to do is a little infrastructure rearrangement.
And a cough drop.